Okay, so today we want to talk about Simpson's paradox. And before we talk about Simpson's paradox, we're going to talk about the independent surface. So you want to think about two random variables, say two coins, or two unrelated things. And we're going to indicate the failure of the first one with a 0, success with a 1, failure of the second with a 0, success with a 1. So, probability that the first coin is equal to 1 is going to be P. Probability that the second coin is equal to 1 is going to be Q. Now, under the model of independence, we know that the set of 2 by 2 tables which represent independence are a surface inside of this thing. So the first thing we should do is figure out what that surface looks like. So there are 4 edges of this tetrahedron, the probability simplex, which are included in the independence model, and there are 2 which are not. So the 4 that are included are this edge, because I can fix the first coin to be 0 and let the second coin vary between probabilities 0 and 1. I can fix the second coin to be 0 and let the first coin vary between 0 and 1. So that's this back edge. I can fix the second coin to be 1 and let the first vary between 0 and 1. That's this edge. And I can fix the first one to be 1 and let the second vary. That's this edge. Okay, so we have a little Pac-Man of allowed distributions on the boundary, and now we want to think about which ones on the interior are part of this variety, and they're all also lines, and you could think about those lines as points. Say I take some value here. This is a 2 by 2 table, and maybe there's a 0.8 chance of getting outcome 1, 1, and a 0.2 chance of getting outcome 1, 0. So the numbering here is 1 and 0. Sorry, 0, 1, 0, 1. So this is 1, 1, and this is 1, 0. That has 0.2, and that's 0, 0. Now, as I vary the probability of, so this was assuming that the first one always succeeds. As I reduce the probability that the first one succeeds, I entertain the possibility that the first one could be 0, and I move down a line. Looks like this. It goes down here to a corresponding point. Now the first is guaranteed to fail, and we have the same distribution on the second. So this point here is the table 0.2, 0.8, 0, 0. And I can continue with lines like that. And I get something called the independent surface. This part here is in the background, this part is in the foreground. It's a bit like a piece of paper that's been rolled like that. And just as the logic here, I could also have picked points along this line and drew them to points along this line, so there's also a ruling that goes in the other direction. Okay, so that's a picture of the independent surface. One thing you can notice about the independent surface is that it splits the tetrahedron into 2 pieces. It's a curved surface. There's an area below the tetrahedron and there's an area above the tetrahedron. So let's see what those areas represent. Let's take a point like that one, right on this line between 0, 0 and 1, 1. This is impossible to reach on the independence model because if there's some chance of this and there's some chance of this and the 2 variables are independent, then there's some chance I'll get one heads and tails, the other heads and tails. So this point here is a table of perfect association. I only get 0, 0 or 1, 1, and I have no chance of getting a mixed outcome. So that's this point. So you can think about that as a positive residual or as a positive association between the 2 variables. Likewise down here, if I look at this point, I get perfect disagreement. So that tells me that the region below this thing, let's reinforce this line. That's in front. The region below this thing is the area in which the two variables disagree. I'm going to get negative residuals. Odds ratios above 1, odds ratios below 1. So that's the picture. And now we can talk about Simpson's paradox. So Simpson's paradox arises from the fact that this surface is curved. Right? So now we've only been talking about 2 by 2 tables. Simpson's paradox is something that happens in 2 by 2 by 2 tables. Well, we want to draw a 2 by 2 by 2 table. Suppose there's another coin. Let's call this variable h and t. Then we have our 2 by 2 zeros and ones, zeros and ones. So a 2 by 2 by 2 table is two 2 by 2 tables. One h table and one t table. So I can think, because this is just 2 by 2 tables, I can think about this as representing 2 points inside this space. So if I want to write a 2 by 2 by 2 table, if I want to write a 2 by 2 table, I give you 1 point in the tetrahedron. I can ask whether it's on the independence space. If I want to give you a 2 by 2 by 2 table, I should give you 2 points in the tetrahedron. So, I could have a table here and a table here. I could have these 2 tables, any 2 points inside. It could be that 2 of these points are both on the region of positive association. It could be that 2 are on the region of negative association. It could be that 1 is on top and 1 is on bottom. Now, if I want to think about the totals of these 2 tables, I have n h++ and n t++. That's the total number of entries in this table, sum over these 4. This is the total number of entries in these tables, sum over those 4. If I think about these 2 tables as representing 2 points in the simplex, if this number and this number are equal, the estimated probability distribution corresponding to this point, so just adding up all 8 numbers and dividing by the sum of these 2, the grand total, is just going to be the point halfway between these 2 tables. That's the average of these 2 tables. That corresponds to the marginal distribution, the marginal where I sum over the first variable. So the marginal association, or the marginal table, sum over first variable, somewhere in the middle. Doesn't have to be the exact middle of this line segment. If nt++ is larger, this point is going to move closer toward t. If this is smaller than that, it's going to move closer to that. If one of these totals is 0, then I just have a 2 by 2 table, and I only really have 1 point. Okay, so the fact that that's what's going on with the geometry is what makes us run into Simpson's paradox. We can have a situation where the H table has a positive association, lives in this region. The T table has a positive association, lives in this region. Yet this curved surface sticks itself between them. And when I draw the line between them, there are some balances of totals between T and H that allow me to push down below the surface. So in this picture, it's a little bit hard to see, but suppose I had one point which is behind the green surface, and I had another point here which is in front of the green surface. I drew a line between them. It pierces the green surface, goes in there a little bit, comes out the other side. The fact that that can happen, that this surface is not convex, that there exist tables below it, means that I can have an average or a mixture of 2 tables up here, a 2 by 2 table, whose marginals, their average point or their weighted average point in the middle, is actually in the region of negative association.